Welcome back. In the last video, we covered birth first search, which were great when every step costs the same. But what happens in the real world where some parts are cheaper, some are more expensive? So that's where UCS comes into picture, Uniform Cost Search. So UCS is essentially an extension of BFS, but instead of expanding nodes based on which comes first, it expands the node with the lowest path cost. So, what is it trying to do? It is considering the path cost, always expanding the least cost node first. This is the key shift in thinking. It's not about how many steps you have taken, but how much those steps have cost you cumulatively. To do this, UCS uses a priority queue. Priority queue based on the path cost, often written as G of n, meaning the cost from the start node to node n. Here at every step, UCS picks the node in the frontier with the smallest g of n value and expands the next node, expands the one that is next. So you can think it as like a GPS app or maps. If you tell it shortest distance, that's more likely BFS thinking in terms of number of turns. But if you tell it you need a cheapest route, so it is factoring in toll roads, fuel cost, traffic delays. That's exactly what UCS does. It's always choose the cheapest path first, not necessarily the one with fewest hopes. Let's take an example. Here, if you see the example for pathcast, here every edge has an associated cost, right? Here they have an associated cost. A to B, it costs 2. Then A to C, it costs 3. Then B to D, it is costing 3. UCS is we can say UCS is complete as long as the costs are non-negative. It will find a solution if one exists. And it is optimal even when the cost varies across the edges. UCS guarantees the cheapest possible path to the goal. So this is actually a very big improvement compared to the BFS. However, this comes with a cost. Its time and what? Space complexity. So as you see here is the complexity where C star is the cost of optimal function and epsilon is the smallest edge cost. It's like in simple terms, if costs are very small and vary a lot, UCS can end up exploring a huge number of nodes, sometimes even more than BFS.
See this example and let us trace to this graph step by step. From A we can go to B with a cost first. Not in B with a cost of 3. From B we can reach C with a cost of 2. You'll see here. Or reach directly to the D with a cost of 2. From C we can reach D with a cost of 5. So now let's run this UCS algorithm on this. Exactly the way the algorithm would. So let's start. We start with the A. So with the cost, at first the cost is 0. This goes into our priority queue. So our step 1 is to expand A. This gives us two options. B with a total cost of 1 and C with a total cost of 3. So these both go into the priority queue. Remember that this is a priority queue. That means the node with the lowest cost, that means B here, always comes first regardless of the order we discovered them in. Then the step 2 here is we check the queue and we know that B is at cost of 1, C is at cost of 3. So B is cheaper. So we expand B next. From B we can reach to C with a cost of 1. Previously it is 1 plus 2. So giving total cost of 3. And we can also reach D with a cost of 1 plus 2. See, if you see from here to here, we have a cost 2. So it is also 3 as well. Now we already have C in the queue at cost of 3 from the direct route A to C. Now our new route to C through B also cost 3, right? So it is a tie basically. So UCS just keeps the existing one, no update needed. We added our new node D to the queue at the cost 3. So our next step is that our queue now has C at a cost of 3, D at a cost of 3. So there is another tie. So UCS can expand either one first. Let's say that it picks D. Since D is our goal, since the search stops here at the moment the D got expanded. So tracing back the path that achieved this lowest cost, we get A to B, then B directly to D, a total cost of 3. This matches the path highlight on the side, that is A, B, D, you can see. So what are the key insights that we can get from here? If you notice that UCS never seriously needed to go to C at all, but the moment it found B leading directly to D with a cost of 3, that became one of the cheapest options on the table, tied with the region C. So this is the essence of UCS. It always expands based on the total accumulated cost, not the number of hops. So a path with the fewer edges like A, C, D at cost of 8, we mean this one, at the cost of 8 loses entirely to a path with the more edges. So A to B to 3 simply because the total cost is lower.